Hello, my name is Michael Amir, and I will be presenting our paper, Multi-Agent Distributed and Decentralized Geometric Task Allocation. Thank you very much, Professor Salazzo, for agreeing to present this paper for us at CDC, and I hope this presentation helps. So let's get started. Um, the problem that we're going to be solving in this paper is a swarm task allocation problem which we solve through the decentralized coordination of a big, autonomous, simple robotic task force. The robots in the swarm must find and fulfill unknown dynamic tasks in an unknown environment, which means that they don't know where the tasks are in advance, and the tasks may change over time. The paradigm that we're going to be working in is the ant-robotics paradigm, which assumes that agents are identical and obey the same dynamic rules. It assumes that agents don't have an ID or a name and can't be addressed explicitly. It assumes agents are memoryless. Decision making is based on current information only. We assume that agent dynamics derive from interaction with others and the environment. We assume that agents may have an infinite or finite sensing range. We assume that agents lack self-location capabilities and a global frame of reference, such as a GPS. And we assume that agents don't use explicit communication for coordination. And so why would we use such a restrictive paradigm? Why are we interested in the ant-robotics paradigm? Well, there's a few advantages to this paradigm. First, it allows for utilization of a large number of agents in a single system because we don't assume that each agent has expensive hardware capabilities. We assume that it only relies on basic capabilities, which would presumably make it less expensive to manufacture. Because the robots don't have as much compute, they might need to carry less hardware on them, and they might need to perform less complex computations, which is energy effective. It enables longer operation. Simplicity is another advantage. Simplicity can be its own goal, and having an elegant algorithm that does something and that we can completely understand is sometimes better than having a complex algorithm that we don't entirely understand. Um, Another benefit of this framework is that it enables real-time adaptation. Agents react to changes in the current time step, and so changing for example, changing the tasks in real time is not a problem for this system. And so robustness is related to real-time adaptation. The swarm maintains its behavior even when individuals leave or join the group because they only operate based on the current point in time, based on what they currently see. They don't have a persistent state that they need to take into account. And so this algorithm is really lends itself to spontaneous changes in the list of tasks. For example, tasks can be added or removed. Swarms, parts of the swarm can crash, parts of the swarm can be added later, and the algorithm will still work. So it's a nice framework for this kind of adaptability. And finally, we want to show some problems can only be solved or can easily be solved with a large number of agents. And so a large number of agents should be inexpensive and energy effective and simple. And so this paradigm lends itself to swarm robotics in the sense that in swarm robotics, we want to solve problems with a large number of simple robots. Definitions and notations. L, we define a region of interest, L, which is a subset of the plane in which there are n agents and k targets or tasks. Nk is the demand intensity of task Tk, which can either represent how many agents are necessary to fulfill Tk, or it can be some kind of measurement of roughly how difficult the task is to fulfill. It depends on how we define our problem. Phi is the demand function and represents the combined requirements of all tasks at a given point. So we define this kind of heat map over the region, which basically the larger it is, the harder it is to fulfill, or the more agents are needed to fulfill a task at a given location. You can think of a forest fire, where there is more heat intensity, you're going to need more agents. Or you can think of a search and rescue task, where if there are 10 people at a given location, you're going to need more drones to take care of them than if there is just one person. PI is the position of the ith agent at time t, and Q of t is the agent constellation at time t, which is the concatenation of all agent positions. Psi of at a give is a function that takes into consideration the current constellation of agents as well as a given coordinate, and it tells you at this coordinate how weak is the agent's coverage. And so remember, the agents are trying to fulfill tasks, which we take as meaning they need to cover those tasks. And psi basically tells us how badly they're covering a given point in the region. So there's a heat map of errors. And so finally, G of Q is the total error function of psi over the region of interest L. And so what G of Q tells us is how much cumulative error there is in the system. And the goal of this paper is to arrange our agents, to bring our agents into a constellation that minimizes G of Q. And so we're going to be covering 3 task allocation algorithms. In task allocation through gradient descent, we assume that both agents and tasks emit signals. The signals of the tasks are information that the agents can use to locate the tasks, or they are otherwise some type of information that the agent wishes to cover. So for example, if you're doing a reconnaissance task, then maybe a point of interest is going to emit at a radius about itself some kind of heat map which represents the locations of valuable information in the area. And the agents themselves emit also a signal. The signal that the agents emit represents the agent's ability to cover and fulfill tasks around them at a given distance. So the agent signal is moving around with the agent. It's centered at the agent and it's moving around the map with the agent. And the task signals are stationary. They form some kind of heat map. And so the goal in task allocation through gradient descent is to cover with the agent signals the heat map generated by the task signals. And this is good for our reconnaissance, information gathering tasks, search and rescue, stuff like that. In task allocation through the electrostatic model, we do something similar. Except we model tasks and agents as electrically charged particles. And so this type of algorithm is more useful when the tasks are discrete in the environment. And so they don't form necessarily a continuous heat map, but they form a discrete heat map, which the agents seek to find the spikes of. And so finally, we solve a task allocation of a scalar field through gradient descent problem. And this type of task allocation problem is most fitted for a situation where your task is something continuous, such as a forest fire, and you want your agents to cover the forest fire in some sense as best they can. And so these 3 models, they can all be solved. They can all be used to solve all of the tasks we outline here, but they can be seen as specialized for different purposes. And so our solution has 3 components. Our idea is that when the swarm doesn't know where a task is, it should just uniformly disperse around the region. And this uniform dispersion is what enables the swarm to find the tasks that it is looking for. And we also say that when the swarm does know where a task is, it should configure itself. Each agent should configure itself, taking into account its neighbor's coverage and the target requirements. And we attain both of these goals by the same mechanism of attraction-repulsion dynamics, where agents repulse each other while targets attract agents. But the interesting thing about this work is that we don't assume attraction-repulsion dynamics. We actually show that attraction-repulsion dynamics are the outcome of an optimization they are the outcome of gradient descent over an L2 norm that we want to minimize. And so that's something that I think hasn't been done before, showing that attraction repulsion arises from an L2 norm optimization. And so, as I said, one of our algorithms is task allocation through gradient descent. And in this problem, we assume that that there is a symmetric signal, which is called d tilde. And this signal is a scalar symmetric function that we place on top of each agent and on top of each task. And so for the task, it represents the desire, or it represents a kind of requirement emitted by the task. And for the agent, it represents the task coverage ability of the agent, its ability to cover points around itself. And so the goal of the agents is to locate in the map, is to use the signals that they emit, the tildes that are located above them, to cover the heat map that is generated by the tasks. And so we want our agents to move such that the heat map emitted by the cumulative signal of all of them approximates the signal emitted by all of the targets. And so it turns out that when you optimize this kind of goal, when you try to minimize the squared error between the demand function phi and the combined agent's spatial coverage, you get an interesting type of dynamics. You actually get attraction-repulsion dynamics, which is dependent on the shape of the signal function that you provide for the targets and the agents. So we don't tell you the shape of the signal. We don't tell you how the demand the targets emit looks like, or how the demand, or how the agents, or what the agent's ability to cover stuff looks like. But given that you specify those things for us, we derive in the paper attraction-repulsion dynamics, where the agents repulse each other according to a function f, and the targets attract each other according to a function f, which is derived from the shape of the signals that the user provides, or that is derived from the physical requirements of the tasks and the physical capabilities of the agents. And so in this slide, we just show a function f, which is the agent spatial coverage or task requirement function. And we show the big F, which is the interaction function that is derived from the small f. And this big F is what's going to dictate the attraction and repulsion forces at a given distance between an agent and target, and between an agent and an agent. This slide is a simulation of task coverage, where we show that indeed the agents are able to spread and find the tasks. The radius that we draw here, the gray circle around one of the agents, is the visibility radius of each agent. So let's move on. Here we have the electrostatic task allocation model. And so this model is another variant of a task allocation algorithm that we can use to solve the main problem of this paper. And in this model, we assign particles, agents are particles that are assigned a positive charge, and tasks are assigned negative charges based on the task requirement. And so the interaction function between agents follows Coulomb's law, which we wrote down in this slide. So yeah, and this is just explicitly deriving the attraction-repulsion dynamics based on the same framework as before. And here's a simulation of task allocation using the electrostatic model. You can see that the agents are still able to find the tasks, even though they have limited visibility, as witnessed by the gray circle around one of the agents, which indicates the visibility range of each of the agents. But you can also notice that the dynamics are slightly different here. So the way the agents spread around is a little less bouncy and maybe a little bit more uniform, which could be good or it could be bad. It depends on the context. This is a dynamic situation where the tasks change over time. And so the agents are still able to find all the tasks without a problem and fulfill them. Here we have a very involved example where we have very many agents and very many tasks, and we show that this algorithm scales up fine. So the agents, even though they have limited visibility, they're capable of finding everything we need and fulfilling the tasks, which we arrange in a plane shape. So finally, we have the task allocation of a scalar field, algorithm, where we, instead of the demand function being derived from the locations of tasks in the environment, the demand function here is something continuous. So it can be like a forest fire, or an information space, right, that the agents need to cover, a probabilistic information space. So here, the idea is that we try to approximate as best possible the demand function by the agent's coverage ability, same as before, but the demand function is not derived from discrete tasks in the environment. And so here I show you an example where the scalar field is a linear function and the agents try to cover it. And so you can see that the agents gather within more density where the scalar function is increased in density itself. Here's another example where the scalar function is a Gaussian, an exponential, and we show that the agents spread around based on the density of the signal. So the paper has a lot of simulations, and where we assume we show decentralized control based on local sensing of oblivious agents without explicit communication. And you're very welcome to view that because everything is online. And we have a YouTube video for all of that. And yeah. And so to conclude, we showcased that simple agents with no memory, limited visibility, and no communication capabilities can efficiently fulfill various types of task allocation algorithms where they try to approximate the coverage demands of a demand function or a demand profile through 3 different algorithms. And so really the message of this paper is that if you have enough agents, even if they're very simple, they can do a lot of very good things, which no agent individually could have done. So they can spread around, and by repulsing each other, they can create this kind of uniform dispersion field where they find all of the tasks. And then by repulsing each other, they can also redirect agents to tasks that have an unfulfilled demand and away from tasks that have a higher demand, and so forth. And so really, this is a rather simple algorithm, but with enough agents, it becomes a very powerful tool. And that's the message of this paper.